Okay. Today I'm going to show you how to do the simulation for point-to-point control, like for this pick and place application. So using two-arm robot, and here's a two-arm robot model. So L1 for joint Q1, L2 for joint Q2, and for a given tip position XY, and you can express x in terms of angle, L1 cosine Q1 plus L2 cosine Q1 plus Q2, y equal to L1 sine Q1 plus L2 sine Q1 plus Q2. And then you can take a derivative on this equation. So there's a dot x d2, dx dt. So it's a dot x do this derivative equal to minus L1 sine 1 and dq dt. So S1 is actually sine Q1, just for short form, and then do this derivative equal to minus L2 sine Q1 and Q2. This is a short form of that, and then that's the dot Q1 and the dot Q2. And if we do derivative on y, then you have dy dt, and then derivative on sine will be equal to cosine. So L1 cosine Q1, okay, the short form for cosine Q1, and then that will be a dot Q1. And here this term will be equal to L2, and sine will be cosine, so Q1 plus Q2, and that will be dot Q1 and Q2. So then from there, you can extract what they call the Jacobian. So the term associated with dot Q1 will be here. And the term associated with only dot Q2 will be this term here. And for y dot, and the term associated with dot Q1 will be this term and this term here. And the other term will be this term, it will be associated with dot Q2. So if we use Jacobi, and then the x dot in this case is a vector. So in other words, there's a dot x and y in the vector form is equal to j times the dot q1 and q2. So this is the vector. And then if you write in infinitesimal way, so because this is dt, right? And dt cancel out, dt will be equal to delta x and delta q. So Jacobi also relate the increment motion of the tip relate to the increment motion of the joint. So with that, we can solve this point-to-point control using what they call the Newton-Raphson method. So problem state like this: if you're given the initial joint angle, all position, and the final position, as well as the threshold, the epsilon, it is required to solve the final angle, the final joint angle. So this is the quadra quotes. So initially you set the initial angle, final position, and threshold. And then before you do iteration, so this is a numerical iteration method. So you set the Q as the initial angle, and you can calculate the tip difference between final and initial. And then you keep checking. Basically, you keep checking this tip distance until the Q you're trying to solve is close to final Q. So if this one is larger than the threshold, which is accuracy, the bound that you define, if it's larger, then you go through the iteration. If it's smaller than this one, which means you find the solution and then you just jump out to this loop. So inside this loop, and you're trying to calculate the increment based on the tip difference. And this is Jacobi I showed you before. Then take Jacobi inverse, so you can calculate the increment, and then you apply the joint angle. So this is for example, you start from the step one. This will be initial joint angle, and adding this increment that you calculate, and it becomes the new joint angle. And then you put back into the kinematic equation and solve the position corresponding to this angle, and then compare to the desired one, the final, the tip position, and you will calculate the difference. And then go back if the difference is still larger, and then you keep updating. Otherwise, if this tip error is smaller, then you define the threshold and then jump out of this loop. And here's the example, and you see here the threshold when I define is small. It's lower, and your solution is kind of not accurate, right? And as you increase the threshold, and the iteration gets more accurate, like here, and this is even more accurate. So in other words, if we use a Newton-Raphson method, as long as you define your threshold high enough, and you will be able to find the right solution. Here is the MATLAB program. So this program is used numerical solution for point-to-point control. And as before, you define the link length, initial position, 1, 1, final position, 2, 2. And because I defined the initial position instead of initial angle, so here you still can use the closed form solution I introduced to you in the last video. You can solve this initial angle here, and then you plot the initial robot configuration, and then use the initial angle as the initial angle for your Newton-Raphson iteration. And then you define so initial position and final position already define input. Then you calculate the difference between the two. And this is the threshold. In other words, the error bound you define here is very low, 10 to the power minus 1. And you can also introduce the counter for how many iterations. And then now you go into this the loop I just introduced to you in the PowerPoint. So first you calculate the Jacobian, and then you calculate the joint angle increment, and then update the joint angle, and then you put into forward kinematics to calculate the tip position x or y, and then you compare with the final, this is a p final, against the current one that you calculate, and then you update your counter, and if then the program will go back to here, see if this one is larger than the error bound you define. If it's larger, then you go through this loop again. And here I use the closed form solution here again to calculate the true final angle, just to check the accuracy. Okay, and that's what I showed you last time. So this is the closed form solution, and then you calculate and then you plot. And then here you get in the numerical final angle, and then you calculate the difference between the final and the initial, and then for joint 1, joint 2. So basically you can calculate the intermediate points, and then you use the for loop again, like the one showed you for the closed form solution. And you can go through the intermediate points, and here you just show on the plot the final error, how many caps. So I'm going to show you here. The first case would be the error is relatively larger here. This one here. So I can show you here. Because the error bound is relatively low, so that's why your final iteration, your error is relatively big, right? So this is the initial position 1, 1, this is the final position 2, 2. But so iteration, your final position is here. So if your error bound is lower, and then your solution will not be accurate. So let's say we increase the error bound. Do it again. So now, obviously, it's getting closer to the true value. Here again, this is 1, 1, this is 2, 2, right? This 2, 2 here, this one here, the arrow is getting smaller, and the first one I show you is just one iteration. This is for 2 iterations, and that will be 2, 2. Right? So then keep increasing the run. Okay, this is more accurate, and then you run again. So this is very accurate. See, the arrow is really accurate. And then this is through 3 iterations. And you can see this is the initial position, and this is very close, right? The final position is very close. Okay. I hope you learned something from this video.